Good morning, everybody. How are you guys doing this morning? I finished grading your tests. Your test grades are already up on RenWeb Facts and also on Google Classroom. So if you go to Google Classroom, you can see any question that you got wrong, which questions you got wrong and all that. Now, I probably don't go into a whole lot of detail. So if anybody has more specific questions about the test, feel free to email me. Okay? All right. So today we are going to continue on talking about gases. Our new unit is all about gases. And as you guys probably did the reading, then you have learned about pressure and all that kind of stuff. So some of that stuff may have been a review of stuff that you've learned before, and some of the stuff is probably going to be new. So this unit is all about gases. So we're starting out talking about pressure in gases, and we're going to continue to discuss various different aspects of gases and how gases behave. Okay? So before we begin, anybody want to, does anybody have any questions? We will go through this entire homework, so that will probably answer your questions if you have any questions about the homework. But how's everybody doing? We got a whopping 2 people online. Nice. All right. Hi, how's everybody doing? So not a lot of people here with us. 3, getting a few more people. Hi, Sarah. And so we will let me just go ahead and I'm going to go through this and then see if you guys have any questions here at the end, that in addition to this stuff. So I posted your new homework on Boyle's Law up on Google Classroom this morning. So hopefully you guys got to see that, and we'll start that. So let's jump right into this homework. It's kind of long, and so sorry about that. It may have been a little bit long, but we didn't have class that day, so I figured you guys could do the reading and answer this as you went on. All right. So number 1, and let me adjust this here a bit. What is pressure and how is it different from force? Essentially, the easiest way to answer this is, in my opinion, just using the equation. Pressure is related to force. It's force over an area. And we use pressure because you have various different reasons. You have things like air and water and other different fluids where they exert a force, but they exert a force everywhere, all over their entire surface, or all over everywhere you're in them. And that way, you can understand that force as being a force that's exerted evenly over a particular area, right? So for example, when you get in water, there's water pressure that's exerted over your entire body, and that water pressure exerted more or less evenly over that particular area, okay? So pressure is force over area, and that's pretty much it. That's going to answer your question. Number 2, at sea level, you have air pressure is about 1 atmosphere, and so you guys are going to be dealing with a few different kinds of units. So 1 ATM, let's see, let me even highlight these units. We're talking about here ATM, and we've got PSI, and we've got inches of mercury, and so we have these different units, okay? So ATM stands for atmospheres, and all of these different units have different reasons for how they're derived, right? And so atmospheres is just a pressure unit that is set to, let's say, at ordinary sea level atmospheric pressure. That's your pressure. 1 ATM is 1 atmosphere, okay? And then let's say your pressure gets to be twice as much as atmospheric pressure. That would be 2 ATMs, twice as much as regular atmospheric pressure. So that's how this was chosen, okay? And then we have PSI. PSI is derived exactly from this equation. This is pounds per square inch. So pounds, let me use a different color here. This is pounds per square inch. And pounds is a type of force, okay? So pounds is a force unit. Not type of, but a force unit, okay? And so oftentimes you weigh yourself in pounds. Your weight in pounds is the force of gravity that's on you. And then square inches is just simply a unit of area, all right? Inches of mercury. And this is probably the weirdest one to you guys at first. Well, where in the world did this inches of mercury come from? All right, and it came from this. It came from, and I'm actually gonna skip to this your new assignment here when I talk about that. It came from a barometer. All right, so your inches of mercury are basically from the whole barometer thing. Right? So what is a barometer? A barometer is something that is measuring pressure, right? It's a tool to measure pressure. And how does it work? And so back in the day, a few hundred years ago, people wanted a way to measure pressure. And a real genius came up with this whole idea. I think it was, I don't even know how to say his name, Tortellini or something like that. I believe he was an Italian guy. And so what he did was he said, okay, well, he took a tube and filled it. So he had let's say a whole bunch of mercury. All right. So let's just call that mercury down there. Right. And he took a tube and filled it with mercury and put it inside there. Right. And so we have here a tube. It's sealed at the end and we have it filled completely with mercury. Well, it turns out that the mercury doesn't just stay there, it goes down some. Well, why does it go down? It goes down, the mercury in here goes down because there's a force due to gravity that's pulling the mercury down, all right? But at the same time, not all the mercury goes down, right? Some of the mercury stays in there. Why? Because there's air pressure that's keeping it up. And the amount of air pressure keeping it up, so all this mercury in here, keeps it up a certain amount, right? And so let me redraw this. After this mercury falls down, what you're left with is a certain, so we have this all filled in here with mercury, okay? And until, let's say, the mercury level comes down to here. This is all mercury in here, right? And what determines this level is the air pressure. And you can measure the air pressure right here. The higher this is, means a higher air pressure around you. And how does this work? Okay, you have two forces that are opposing each other. You have the force due to gravity that's pulling down, and you have air pressure, or atmospheric pressure, air pressure, that's pushing up. So the air pressure is all the time bumping into this mercury. As it's bumping into this mercury, it pushes the mercury up this tube, okay? And you have gravity that's pulling this mercury down, right? As gravity pulls down and air pressure pushes up, they come to a balance, and where they balance that, this measurement here is the pressure, the atmospheric pressure, okay? And you can literally use this. You can have this kind of thing outside. As the air pressure goes down, right, this level of mercury is going to go down, and you can say, okay, well, we're going to have a bad weather because the pressure is going down, right? Or if you have a particular high pressure, this is going to go up. It's going to go up and down, up and down. And what you notice that on a normal, non-stormy day at sea level, it was a fairly constant amount, and that's your atmospheric pressure, and that is going to be, I believe, oh shoot, I forget, it was like 29 point something. Does anybody remember what that is in terms of inches of mercury? I gotta look this up real quick. I forget what it was because I don't have the article in front of me. So let's go. Oh, I'm so sorry. Camera's crooked. My bad. So sorry. So 1 ATM, 2 inches of, I don't know. Just a second here. .92. Okay, so sorry about this. This is 29.92 inches. Or you could measure it in terms of millimeters, which you'll see this sometimes. It's 760 millimeters high, right? And so you have two other units of air pressure, and that is inches of mercury or millimeters of mercury, right? And that's simply because of based on this barometer. So that's where we get these units from, right? So back over here. So that's how a barometer works. So back over here, ATM is just simply set to atmospheric pressure. PSI is pounds per square inch. And inches of mercury comes from a barometer. It's measured directly off of a barometer. And so oftentimes, if you're actually reading your weather in America, they'll give you the pressure in inches of mercury because it's coming from a barometer. And so they'll just literally give you that number, inches of mercury. Okay? So let's go ahead and do these conversions. Right, you got 1 ATM, we're going to convert that to PSI, and so we already know, well, 1 ATM is, and that should be directly in that article, it said 14.7 PSI, and in inches of mercury, I believe that's 29.92 inches of mercury, okay? And so that's what your atmospheric pressure is in these different units. Now, what if we have something that's less than 1 atmosphere? In fact, on the top of Mount Everest, the pressure goes all the way down to 0.3. That's crazy, right? So that's like less than 1/3 the normal air pressure. So you're getting a whole lot less oxygen way, way up there. Okay, so how do we do that? We go 0.3 ATM, do your conversions to PSI, and we have 1 ATM is 14.7 PSI. That's going to get me 0.3 times 14.7, 4.41. That's PSI. And convert 0.3 ATM to inches of mercury, so same thing. We're going to go 0.3 ATM. And that's going to be 29.92 inches of mercury over ATM. 0.3 times 29.92 is 8.976 inches of mercury. And we can, of course, round that for significant figures and all that, but I think we'll just leave it for now. Okay. Convert, last of all, we're going to convert 10 PSI to inches of mercury. Now, when we're going from PSI to inches of mercury, there's 2 ways we could do this. We could do this in a 2-step fashion, or check this out. This is going to be the easiest way to do it. So we get 10 PSI, and we don't have any direct conversion from PSI to inches of mercury. So what do? Well, we know from this up here that 1 ATM is 14.7 PSI and 1 ATM is 29.92 inches of mercury. So we can say that these two are equal, right? 14.7 PSI equals 29.92 inches of mercury. And we're going to put one of these on the bottom. If we're starting with PSI, we're going to put this 14.7 PSI on the bottom. And if we're solving for inches of mercury, we're going to put 29.92 inches of mercury on the top. And that is going to be 10 times 29.92 divided by 14.7, 20 point, let's just round that up to 20.4. 20.4 inches of mercury. All right, any questions so far, guys? All right, if you guys have any questions, feel free to stop me. I'm going to go ahead and go on. So the rest of these are not conversions. And so we have here calculating a pressure. Calculate the pressure in PSI exerted by 300-pound man. Practical question, right? Do you want to get stepped on by a large man who's got a really big foot? Or do you want to get stepped on by a small woman who has stiletto high heels, right? So practical question, which would be more painful? Now, force is able to push you, is able to push things or pull things, but pressure is what actually can break your skin, what actually can hurt you. So pressure is a more important gauge of how dangerous something is to your body rather than force, right? And so really, when they talk about boxers or something, they should talk more about the pressure rather than the force that they exert, right? That would be more applicable to how much damage they can actually do. because force can only push you, whereas pressure can actually hurt you and damage you. So let's do this. Pressure is force over area, and force, so this 300 pounds, this is the force of gravity on you or on this person, all right? So a weight is not just the amount of stuff you have, it's also the force of gravity that's acting on you. So that is a force, pounds is a force. So we get 300 pounds, and when he steps on you, we got a contact area of 8.5 square inches, which is basically your whole, he steps on, pretty well right on your foot. 8.5 square inches. Now, of course, in reality, people are rarely going to ever put their entire weight on you, maybe only half their weight on you, but we're just going to say, okay, let's say he puts his entire weight on you, okay? So let's do that calculation. 300 divided by 8.5, and that's going to be 35 psi. Now, 35 psi, you're going to feel it, but it's not nearly close enough to break the skin. 35 psi, okay? And besides, you have also shoes on and all that kind of stuff. It's going to be annoying, but it's not going to be terribly painful. Okay, let's see. Next up, number 4. Now, obviously, if he managed to only get, let's say, your toe, then it's going to be a smaller surface area, and then that's going to hurt more. But whatever. Calculate, now this person, this individual has not just high heels, but really those ones that are really, really sharp, right? And let's suppose that sharp end gets right on your foot, and she puts her entire weight on you. Well, let's going to see what's going to happen, right? So force over area. Her force is a lot smaller, 125 pounds, but the contact area is super small. And this is a realistic number for those stilettos, okay? Realistic number here, right? So 125 divided by 0.175 is 714. That is enough to break skin here. Now, I don't know if it's going to, depends on what kind of shoes you're wearing. If you were wearing like, steel-toed shoes or something, maybe you'll survive this. But, if not, this is going to break skin. That's going to be painful. It's going to go, maybe even enough to, I don't know. But it's not going to be pleasant. All right. So there we go. And it really depends. The exact amount of pressure to break skin is going to depend on what part of your body this is and what clothes you're wearing over top. So I think anywhere from 100 to 200 is the range of where the required PSI required to break your skin. So if you have soft skin, particular area, 100 PSI is enough to break it. If you got tougher skin, maybe 200 PSI, but 700 is certainly enough to break skin there. All right, number 5. We've got the pressure that you exert. So you're going to just do your own calculation. For this one, you could calculate it first with 1 foot and then 2 feet. That's going to be easier. So let's just do a random, no, this is going to be different for every single person. But let's just do a random person, and let's just say, okay, let's say you weigh 200 pounds. And what you do for this calculation is, well, how do you calculate the area of your foot? Well, what you can do is everybody should at home have a ruler of some sort, right? And you can, let's say, trace your foot or just measure your foot, and you can estimate, say your foot is about a rectangle, okay? Now, I know your foot is not a rectangle, but approximate it as a rectangle, and then let's suppose your foot is, let's say, 11 inches long, right? And then, I don't know, maybe 4 inches wide, something like that, okay? But again, we're approximating it somehow. And then you could say, okay, well, 1 foot in that case is going to be 44 square inches, okay? And you're just approximating your foot like this, okay? 11 inches, maybe 4 inches. And it's very, very rough approximation, but it's more or less going to be okay. And it's going to make a big difference as to whether you're wearing shoes or not, all right? Maybe maybe this is 4 inches is not so good. Maybe it should really only be 3 inches. Who knows? But let's just go with it, okay? So let's say it's 11 by 4. That's going to be 44 square inches. And so then when you're on 1 foot, it's going to be, your pressure is going to be 200 divided by 44, so 200 pounds divided by 44 square inches. Or if you're on 2 feet, it's going to be 200 pounds divided by 88, right? 2 feet is going to be twice the amount of area. And so your pressure is going to be less with 2 feet. 1 foot, 2 feet. Okay? So for numbers 3 and 4, say, wait, why did you square it, but the answer you gave wasn't squared? Square for number 3 and 4. 3 and 4, 3 and 4. You mean the squares here? These are already areas. So 8.5 square inches, that's already an area. So we don't need to square anything. In this case, in number 5, we're multiplying the 4 inches by the 11 inches to get an area, 44 square inches. But I've already done that for you guys in 3 and 4, right? So this is a square inches and this is a square inches. And so that's an area, that's an area. So you don't need to do any squaring there. Okay, so these are going to be fairly, reasonable numbers. You can go ahead and do the calculation if you want, but everybody's going to have different numbers. And so I'm not even going to bother getting the number. That's how you do the calculation for number 5. All right. You got to really approximate, and you can, if you wanted to make it more complex, you could have and try to figure out the area of your foot, what it actually is. But it's easiest to say, okay, my foot's a rectangle, and then be good with that. Now, number 6, why does a sharp knife cut things more easily than a dull knife? There's 2 basic ways that you can answer this, but they all have to do with pressure. And the idea of pressure is what cuts, right? Not force, okay? And what happens for the sharp knife is, so if pressure is force over area, the sharp knife has a smaller area. And this is just like the large man, small woman kind of deal right here. So your sharp knife has much smaller area. All right, and these things can be measured, but we're not going to go ahead and do that. All right, you can actually look and see what is the contact area of a sharp knife versus dull knife. Right, in a sharp knife, you've got only this very, very small contact area right there. Right, on a dull knife, it might be something more like this. Right, and you have a much larger contact area. And so basically, because you have a smaller contact area, you need less force in order to create that pressure that cuts something, okay? So the first way to explain it would be a sharp knife has a smaller area, so you need less force in order to cut something. Another way to answer it would be more or less the same idea, but would be this. So if you have the same amount of force for a sharp knife and a dull knife, the same amount of force is going to cause a greater pressure for the sharp knife because the area is smaller. So same force causes a greater pressure for a sharp knife. And either way to explain that is going to be perfectly fine. But basically just the key difference is that contact area for a sharp knife is going to be smaller than it is for a dull knife. Okay? Any questions on the front page? All right, onto the back page or second page. Let me see if I can find mine. Article number 2. What causes air pressure? And I'm probably not even going to write all these down. Let me just go ahead and tell you guys. What causes air pressure is gas particles bumping into things. Gas particles are always moving around. When they bump into things, anything bumping into things, that is a force, right? So all these gas particles are always bumping into stuff. That is exerting a force, and that is what causes your air pressure. Gas particles bumping into things. Number 8, suppose you have some air in a sealed container. If we heat the air, the particles start to move faster. Remember, higher temperature means particles move faster. Okay, so how's that going to affect the pressure? The pressure is going to go up. Why? Because if the particles are going to move faster, they're going to be more collisions and more powerful collisions. Okay? So if they move faster, right, we're imagining these gas particles move around faster and faster and faster the higher you raise that temperature. That's going to mean they're going to be bumping into stuff more often. And when they bump into stuff more often, they're going to cause a greater force and a greater pressure, right? If you have faster particles, they're not just going to move faster and bump into more often, but they're also going to have more powerful collisions, right? If you can think of a car accident, the faster you go, the more dangerous that car accident is. So the faster these gas particles move, the more powerful they're going to collide into things. So both of these things means as you increase the temperature, the pressure goes up. And I want you guys to know that in general, right? As the temperature goes up, the pressure goes up if you keep everything else the same. And that's because of this. Next question. Suppose you keep the temperature the same, but you add more air into the sealed container. So if you add more air, well, what's that going to do? That means you're going to have more air means, right, more air means you're going to have more particles, and so you have more collisions. And that means your pressure is going to go up. Okay? So as your amount of air increases, the pressure is going to increase too, because you're going to have more collisions. All right? Next up, why don't we notice air pressure most of the time? And this is the one question, very interesting, that the article got wrong. Okay? And so if you answered something like, you don't notice air pressure because the air pressure is all around you and is equal on the top and the bottom, that's the wrong answer. It's wrong, well, partly because the pressure on the top and the bottom is not exactly equal, but more importantly, that's not why we don't notice it, okay? Let's suppose you stick your hand on the road and a car rolls over top of your hand. Well, guess what? There's going to be pressure from the road on your hand on the bottom, pressure from the car tire on the top, and those two pressures are going to be equal, right? But your hand is still going to get crushed. Your hand is going to get crushed because the pressure on the top and the bottom are still equal, and they don't cancel each other out. And the same thing with air pressure, okay, guys? So if, let's say, all of a sudden I put my hand into some place with a very large air pressure, your hand would still get crushed, okay? So it doesn't matter that the air pressure is the same on the top and the bottom. That's not the answer. So the article actually got it wrong, okay? So why? Why? What is actually causing us not to notice air pressure? And that's not because air pressure is the same on the top and the bottom and the left and the right. It's because we have pressure inside our body. And that pressure inside the body is going to be approximately equal to air pressure. And we can notice when the pressure inside our body changes. When you go up a mountain, what happens? Your ears pop. And your ears popping is your body's way of changing its internal pressure. Okay? And when it changes internal pressure so that it can maintain this equality where the pressure inside your body is equal to the air pressure. Well, how do you have even pressure inside your body? Well, you have cells, and all your cells have pressure inside of them, right? The pressure is caused by inside your cells. You have air inside of your cells. You also have water, right? And you have other stuff. And those other stuff, those water molecules are bouncing around all the time. The air molecules inside your body are bouncing around all the time, causing pressure inside your body. The pressure inside your body is equal to the pressure outside your body, okay? And that's why you don't notice it. Now, if you ever go scuba diving, ever go deep sea diving, you will notice that the pressure will increase all around you. And how can you take care of it? When you're scuba diving, you breathe in more of that air, and that scuba air the air in your scuba tank is going to dissolve in the blood in your body, and it's going to increase the pressure inside your body. So you need to make sure you go down slowly so that the pressure inside your body increases as the water pressure increases all around you. Okay? Let's suppose, for example, you go out in a spaceship, right? And you decide to open a window, well, obviously opening a window would be bad. And so let's suppose you just put your hand outside the window in a spaceship, okay? What's going to happen to your hand? Well, besides it being super cold and your hand maybe freezing, before that ever happens, you're going to have a bigger problem. The pressure in outer space is essentially zero, okay? And you have pressure inside your body, right? Your cells have pressure, all your blood has pressure, all that has pressure. And what's going to happen is that pressure inside your body is going to force its way out, and probably your hand is going to explode. Your blood vessels are going to blow up, right? Because they have pressure inside, which is not being equaled by outer space, which has no pressure, and your hand will explode in outer space, okay? So we know that there is pressure inside your body, all right? And that pressure inside the body is more or less equal to the air pressure. And that's why you don't notice pressure most of the time, because of the pressure inside your body. All right? Next, what causes air pressure to decrease as you go down a mountain? There's a couple ways that you could explain this. Let's see. We're going to draw. Okay? So this is a mountain. I know, it's a terrible mountain. But when you go up a mountain, there's two main different ways that we can kind of make some sense of this. All right, there's air all around us. Okay, these are going to be air particles. Okay, the first way to understand this is down here at sea level, you have a lot more air above you. And gravity pulls down that air, and because you have a lot more air above you, that more air is going to cause more air pressure. As you go up a mountain, you have less air above you. Even if you go up a little bit, you have less air above you. As you decrease the amount of air above you, that's going to decrease the pressure. The second way to think about this is that as you go up a mountain, the pressure or the gas particles are going to be further apart. They're going to be less the air density is going to be lower, right? As you go up a mountain, you have less and less air, right? Because your gravity is pulling air down closer to the surface, okay? So as you have air spread further apart, that's going to mean your air particles are going to have fewer collisions. They're going to bump into you less often, causing less air pressure. As you're down near the surface of the Earth, near sea level, the gas particles are going to be closer together, and that's going to mean more collisions and higher air pressure. Either one of those explanations is perfectly fine, however you want to explain it. Buoyant force. Buoyant force is a force, an upward force on you, right? Force on, within a fluid, whether it's in air or in liquid, causing things to go up. And what causes it, and this is very interesting, what causes it is the same thing as number 11. You have, in any object, there's a greater pressure, below the object than above the object. Okay, so everything has a buoyant force on it, okay? And that's simply because there's a greater air density, a greater air pressure below the object than above the object, and the difference is small, but it's enough to create this buoyant force. Most things don't notice it, right? You don't float up in the air because, well, you're fairly dense, okay? And most objects don't float because this buoyant force is fairly small, okay? The buoyant force in water is much, much greater, right? And that's because the density of water is greater. Well, you only notice the buoyant force when you have something that's less dense than air or less dense than whatever fluid it's in. So you notice for helium, because helium is less dense than air, and then all of a sudden the buoyant force is going to be greater than the force due to gravity. But everything has a buoyant force on it because everything has greater pressure below the object than above the object. Number 13. And we're going to have to jump over to the homework here in a minute. So I'm going to go through these fairly quickly. What would happen to an empty plastic bottle if you removed all the air, right? It would be crushed. Why? Because the pressure inside would be 0, pressure outside would be great, and that outside pressure would crush it. It would force it to be crushed, okay? So removing the air would cause the pressure to be 0 on the inside. Number 14, explain why helium and hot air balloons rise. And I don't have time to get into a whole lot of detail, so let me just quickly say, helium balloons, we already said that they have their weight, right, the force due to gravity on them is going to be less than the buoyant force. Okay, the buoyant force is caused by the pressure below an object being greater than the pressure above an object, right? That's going to be upward. But because the helium balloons are so light, right, they have such a small density, therefore the force of gravity of them is less than the buoyant force, causing them to go upward, right? Hot air balloons, a little bit more complicated. Basically, as you heat up the air inside the hot air balloon, what happens is the gas moves around faster. And when the gas moves around faster, then the air goes out of the balloon, right? Because the air is now hotter, it's moving around faster, it's spreading out, right? Hot air spreads out, it moves faster, and it causes air to go out of the balloon. Once the air goes out of the balloon, then all of a sudden the balloon is going to weigh less than the displaced air. So that's going to cause the force due to gravity being less than the buoyant force, and it's going to rise. Okay? So I'm going to go ahead, I know we don't have a whole lot of time left, so I want to go ahead and jump right into the new stuff. I wish we had more time. I'm sorry that homework was a little bit long. So we only have about 5 minutes, and I'm going to cover this kind of stuff. So we already talked about the barometer, right? But I do want to talk about number 3, and then that's going to allow you to answer all the rest of the questions. So there's, let me see, all the questions, all the other questions besides like, so 2, 3, 4, 5, 6, 7, they're all dealing with the same thing, and that's Boyle's law, okay? So this and all of these is Boyle's law. And what is Boyle's law? Boyle's law is kind of related to what some of the stuff that we just talked about, and that is that as the, and I'm going to run out of space here, as the pressure goes up, the volume goes down for a gas. Okay, so you have a gas. If you increase the pressure, the volume is going to go down. Or you can understand this the other way. You can either understand this as compressing. If you just take some weight and press on some kind of piston or some kind of contained gas, you're going to increase the pressure, the volume is going to go down, right? Or you can understand it as the volume goes down, the pressure goes up. What do I mean? So if I decrease the space of a gas, all of a sudden that's going to be what? That's going to be more collisions, right? More collisions. And more collisions are going to make the pressure go up. So if you decrease the volume, if you give a certain amount of gas less space, it's going to collide more often, causing the pressure to increase. Okay? So Boyle was a pretty cool guy, is one of the guys that's known as the father of chemistry. There's actually 3 different guys, at least 3 different guys that I know of that are known as the father of chemistry. He's just one of them. And he was super cool because he essentially helped people to transition from the alchemy age to the chemistry age, because he's published all of his results. Right back when we had alchemists and during the Dark Ages, nobody published any of the results. Everybody kept everything a secret. They were all trying to do cool things, and they were all able to discover new things, but science didn't progress because everybody wanted to keep everything a secret. What Boyle did was he started a society for scientific publications, and when they had these scientific publications, now all of a sudden chemistry turned into a real science, right? And everybody was able to learn from everybody else, and we were able to progress. And so publication is super, super awesome for that. So anyway, on to what is Boyle's law. Let's mathify this, all right? We want to know this in terms of an equation, and so the equation is this, and that is P times V is a constant. So this is Boyle's law. The pressure times the volume is going to be equal to a constant. Well, what does that mean? That means as the pressure goes up, the volume must go down in order for this product, pressure times volume, to be a constant. And so we can turn that into a usable equation like this. So if pressure times volume is a constant, that would mean P1 V1 equals P2 V2. All right? This is simply just pressure at time 1 and volume at time 2, pressure at time 2 and volume at time 2. Okay? So pressure at time 1, volume at time 1, this product of P times V is going to be equal to P times V later on. So then we can just use this equation for any of these problems. Let's go ahead and do it here. What is the pressure if the gas expands to 100 milliliters? So we have, let's identify everything here. We have a 30 milliliters of gas. This is going to be V1 in a piston, has a pressure of this. This is going to be P1. What is the pressure? So we're solving for pressure if the gas expands to this. This is going to be V2. So how do we solve this? If we're solving for your volume, we're going to be solving for V2. Sorry, no, we're solving for pressure. We're going to be solving for P2. So P2, you want to know what that is. Then we want to get P2 all by itself. So what do? We just divide both sides by V2. That's going to mean V2 over V2 cancel out, and the equation becomes P2 equals P1 V1 over V2. Plug in some numbers here. P1 is 2.75 atm. V1 is 30 milliliters. Let me move this up so you guys can see. V2 is 100 milliliters, and let's do the math, and then we'll be done. We have 2.75 times 30 divided by 100, 0.825. 0.825. And the question is, what are the units? Well, we can look over here. Milliliters over milliliters cancel out, so the units must be ATM. Okay? You can do this with any kind of units as long as your units are going to cancel out. If, let's say, you have milliliters and liters, you're going to need to make sure you convert them to the same units. You have to have the same units on the top and the bottom so that they cancel out. Okay? I think that's the case for most of them, but be careful at number 7. Number 7, the last problem, I think you need to do some unit conversions on that one. So guys, we are just about completely out of time. So I'm going to let you guys work on the rest of these. Make sure you guys, for your homework, have Boyle's law. And let me write Boyle's law right here at the top again. Okay? So you can have it as PV equals a constant, or you can have it as P1 V1 equals P2 V2. That is known as Boyle's law, and that's the equation that you're going to use for all of these problems. Okay? So see you guys. Have a great rest of the day, and see you to, you know what? I think we're not going to have a live stream tomorrow. So see you guys on Wednesday. All right. The homework is going to be due Wednesday, not tomorrow. I'm just going to make it due Wednesday. So you guys have a couple days to work on this. So homework due Wednesday, no live stream tomorrow. Have a great rest of your day. Have a great day tomorrow. And if you guys have any questions, feel free to, send me an email, anything like that. All right. See you guys.